Okay, now we're going to talk about irrational numbers. We've been talking about rational numbers. Remember, rational numbers is any number that can be written like A over B, a fraction. But now we've got irrational, not rational. So that's numbers like this. So the square root of 25 is read the square root of 25. It means we're looking for a number that when we multiply it by itself gives us 25. Okay, so that would be 5. The square root of 25 equals 5 because 5 squared, or 5 times 5, is 25. The symbol, this part, is called the radical sign. The number underneath the radical sign is called the radicand. Okay, all together we call these radicals. Okay, we're only going to talk about the principal, or in other words, positive square roots. Think about this. -5 all squared, -5 times -5 is also 25. So technically, the square root of 25 is +5 and -5. But we're going to talk about the positive one's called the principal root, and that's all we're going to consider. Okay, now, talking about the negatives, if we have a square root with a negative underneath the radical, we're going to say that's not a real number. Think about this. What if the negative was underneath the radical? I would need two numbers. That's the same number, right? That when you multiply it by itself, it gives you -25. Well, +5 times +5 is +25. That doesn't work. -5 times -5 is +25. That doesn't work. It'd have to be +5 times -5, right? But that's not the same number. That's not times itself. So when you get in upper level math, you'll talk more about these. For right now, we're just going to call them not real numbers, okay? They belong to a different group of numbers instead of the real number system. Okay, so let's practice some of these. What is the square root of 16? That means we want a number that when we multiply times itself, it gives us 16. Because 4 times 4 is 16, the square root of 16 is 4. Now here's something really interesting, and we'll talk about in more detail later. Let's say we had the square root of 49 over 36, right? And you're thinking, oh my word, a fraction. But because of the way fractions work when you're multiplying them, you just multiply straight across numerators, straight across denominators. Really, I can do the numerator and denominator individually. So I can think, what's the square root of 49? What number multiplied by itself gives 49? 7 times 7 is 49, so that's my numerator. And square root of 36, because 6 times 6 is 36, that's my denominator. So I don't have to think about this as, oh my word, what fraction multiplied times itself gives this fraction. I can do the numerator and denominator individually. Okay, so what about one like this? Square root of -121. Uh-oh. Soon as you see a negative underneath a radical, we just say, not a real number, not a real number, and I'm done, right? If the negative is underneath the radical. But be aware, it's okay for it to be outside the radical, like this, right? This just means I want the negative of square root of 81, which is what? Right, 9, because 9 times 9 is 81. So if it's outside the radical, your number's it's just going to stay there. It's going to be negative. If it's under the radical, not a real number. Okay, adding and subtracting radicals is like anything else. The only thing you can do is combine like terms. Remember when we were talking about adding x's and y's? You can't add x plus y. And if you had 2x plus 5x, well, you say that's 7x's, right? You add the numerals and the variable part stays the same. Same thing with radicals. If you had 3 square roots of 5 plus 1 square root of 5, right? I don't really know what a square root of 5 is. I mean, I know it's 2 point dot 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 some number. So they might as well be an x. 3 of them plus 1 more, well, that gives me 4 of those square root of 5 things, whatever they are. Notice the radical part didn't change. Just like over here, the x part didn't change. I'm just saying how many of them I have. So if we had 12 square roots of 7 minus 8 square roots of 7, as long as the radical part is the same, then I can combine them. Oh, 12 of these things, whatever they are, minus 8 of the same things. So 12 minus 8, that'll give me 4 of those things, which in this case happens to be square roots of 7. So adding and subtracting radicals, as long as the radical part is the same, is really easy. Okay, so that's just a little bit of introductory business. You might want to make yourself a list somewhere of all your perfect squares so you'll recognize these numbers. In other words, make yourself a list somewhere while you can't use it on a test, but while you're working on your homework and getting used to recognizing these numbers. And you can't start out with this on the test, but you could make one once you started the test. You could make your own chart if you wanted to. 1 times 1 is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36, and on and on and on. You will be expected to recognize your square numbers up to about probably 13. Okay, so 9 squared is 81. 10 squared is 100. 11 squared is 121 in case you need these. 12 squared is 144. And 13 squared is 169. So you might want to make yourself a list somewhere. Oh, it changed my color. Okay, let me know if you need anything at all.